Good day, everybody. You are welcome once again. This is Turning Point Tutorial, and today we are considering physics, and we are considering a part very important in physics too, and that is physics 001. We are dealing with a topic in mechanics. And we know, remember last time we have dealt with the equations of motion, and we want to move forward to consider the motion under gravity, that is upward and downward motion. As you can see here on the board, motion under gravity, the upward and the downward motion. Now you remember, have it in mind that a body falling from a height towards ground level experiences a constant increase in velocity as a result of acceleration. That the body actually experiences acceleration due to gravity. That is the acceleration due to gravity. Now also have it in mind that at any point in time, a body that is thrown to move upwards experiences a uniform retardation due to gravity. Or in other words, you can say when a body is thrown upwards, the acceleration of the body will be negative. Why? This is because the direction of the gravitation of the earth, that is the gravitational pull of the earth, is acting downwards, whereas the body is accelerating again towards upwards, and its acceleration is against the direction of the acceleration due to gravity, or you can call it the gravitational acceleration. Once again, I said gravitational acceleration acts downwards, but if a body is thrown upwards, the acceleration of the body is actually against that of the gravitational acceleration as acting downwards. So we can say at that very point, the value you have for the gravitational acceleration will be negative, minus g. And remember, gravitational acceleration actually is always represented by small letter g, and then you have it will be minus g, that is a body thrown upwards. Then on the other hand, when a body is falling freely from a height, falling downwards from a height, what happens? It will actually experience a kind of is experiencing a kind of acceleration that is in line with that of the gravitational acceleration. That means it is actually falling, its own acceleration is moving towards the direction of the gravitational acceleration. It is in line with the gravitational acceleration, so we can say it will experience a positive acceleration. Let's say here, if the acceleration, now you know quite well that the acceleration is g, small letter g, and then in that very case it will have a positive acceleration, positive g. Now we can say once again, remember I said before that at any point in time a body is thrown upwards and is thrown downwards, that is called what? That body is always experiencing a kind of motion. Its own motion is being affected by gravity. So all this kind of motion, we say that they are under gravity, motion under gravity. Gravitational acceleration is brought about by the force of attraction of the earth on bodies around it, and it is always denoted by g. And then with the value, you consider the value of gravitational acceleration is always approximately 10 meters per second squared. It's always approximately 10 meters per second squared, or like this, 10 meters per second squared. That is the approximation or the approximate value of gravitational acceleration to gravity. Now we want to come to some important things that we need to look at. When the body is thrown upwards or downwards, then the equations of motion will be changed, adjusted into a new way or into a new pattern. It's actually the same, but the values will change. Some of the values or these parameters will be changed. Like for instance, when you consider the first equation of motion is v is equal to u plus at, and the second equation of motion, which is the s is equal to ut plus half at squared, and then the last one, which is v squared, equals u squared plus 2as. Now these three equations of motion will have to adjust their parameters. And what are the parameters we should actually adjust? Now take note, when a body is thrown upwards and it gets to the highest height, then understand this, v will be equal to 0. And when a body is thrown is falling freely from a height, when the body is falling freely from a height, then u will be equal to 0. What is v? Remember that v is our final velocity. And then when the body is falling freely from a height, the initial velocity is always 0. But when the body is thrown upwards, then the final velocity will become equal to 0. Then what we consider once again here is at any point in time when a body is thrown upwards and then it falls down, the time it takes the body to get to the maximum height above the ground, and the time it will take the body to fall from the maximum height to the ground level will be the same. That means time to move up and the time to come down will be equal. Then let's consider what are the changes here. From the first equation of motion, when the body is thrown upward now let us consider it very well separately. Upward motion, the body thrown upward motion, what will happen? This equation of motion now, this first equation of motion will be adjusted to be now v equals, what is here? U, a body thrown upwards, what will happen? The u will remain the same. The initial velocity remains, actually it will not change to 0, but the final velocity will change to 0. So we have u plus at, but then what's here now? The v becomes 0, the final velocity becomes 0 because it's been thrown upwards. Then here the u remains, will retain its value, but what we have here, the acceleration is not ordinary linear acceleration, it will be actually affected by gravity, acceleration due to gravity. For this reason, it will be minus g. Why is it minus g? Because we know quite well that when the body is thrown upwards, the acceleration due to gravity will be minus g, negative. Then we have our time still there too. What we have finally here will be 0 equals u minus gt, plus times minus is minus, and then we have g times t, gt. At the end of the day, it implies that u is equal to gt when you make your u the subject formula. Then that is the other way. For the other one, we have this second equation of motion. Remember we said that u, when a body is thrown upwards, u is still there, the value of u is there, and the acceleration becomes minus g, negative. And then at the distance now will change to h. The distance now becomes h. What's the h now? The vertical distance. The vertical distance, which is called the height above the ground. The height above the ground is called the vertical distance, and therefore instead of writing the linear distance, we have the vertical distance above the ground, which is the height. So anyway, wherever you see s, it becomes h. Here we have h equals ut plus, then the half, here we have half, then the g, which is the a, which is minus g in bracket, then we have t. H, therefore it implies that h equals ut plus and minus, you have minus, then you have half gt squared. Here we have this is what is half gt squared. This h is equal to ut plus half, then you have minus g, then t squared. Then the other aspects, you can call this one equation 1 as equation 1. You can call equation I. You call this one equation II. Then for the third one, we can have it this way. The V is 0 because it's upward motion, thrown upward. V here at the maximum height changes to 0 at the maximum height. So we have U 0 squared equals, then U squared, then plus 2, then the A is negative minus G, then the distance, which is the H, height above the ground. Everything becomes, it implies that 0 equals U squared plus, then plus times minus gives us minus 2, then G H. And at the end of the day, what we have now, making your U the subject formula, you have U squared equals 2GH. And at the end of the day, we have, it implies that U is equal to 2, U equals 2GH, and the square root of 2GH. Then we have this one to be equation I. Then let's consider the aspect of the downward motion. For the downward motion, that is when a body is thrown, is falling freely from a height, above the ground. What are those things we should consider? Now take note. The initial velocity U is equal to 0. Then the final velocity will still be there, and it cannot be equal to 0 then, because it gets to the ground with a full force. So the final velocity cannot be, it was actually not retarding. Then we have to understand here that our acceleration due to gravity will be positive because it's in line, it's according to the direction of gravitational acceleration. Then we can say here is positive. Then for the distance above the ground, the vertical height, which is the distance above the ground, which is the S, become equals to H. Then we consider this equation 1, equation 2, and 3 again. When we consider these three equations, we'll have a new form of it, a new pattern or a new way of approach. For this one, equation 1 changes to V, as we have V equals U plus AT. Well, what we need to do right here, our U is 0, so we have V equals 0 plus A. The A now is positive, so positive G, so GT. Therefore, V equals GT. Now, let's call this one equation IV. Then from this one, we have second equation, which is S equals UT plus half AT squared. The S here is our height. It implies that the S, which is the height, is equal to, then the U is no height is 0, so 0 times the time plus half. Then this is a positive G, this is the A becomes positive G, T squared. At the end of the day, it implies that our height, now 0 times T, 0, and that cancels out, becomes half GT squared, and that is equation 5. Then from this one, we have, remember, V squared is equal to U squared plus 2AS. Now, for a free falling body, a body falling from a height above the ground, falling freely or released, then what do we say? The U is 0, initial velocity is 0. V squared is equal to 0 squared plus 2. The A becomes G, and the S becomes H. And at the end of the day, we have V squared is equal to 2GH, because 0 squared is 0, and that cancels out. It implies that our V squared is, when you take the square root of both sides, we have V equals 2GH, and that's equation 6. Equation 6. Now we have seen the various types of equation of motion. Now this one is based on upward and downward motion. Based on upward, for the upward motion, we have it this way: this, and this. Equation 1, 2, and 3. Then for the downward motion, we see here 4, 5, and 6. But if you understand this, there are some cases where we have to throw, in the case of the upward motion, we throw an object upward, and then if we consider a case whereby it is not going to get to the maximum height, if actually we are not considering that of the maximum height, then we can just leave it this way by saying that for this one, we can just say that V equals U plus then minus, then we have GT. Then for this one remains this. Then for this one remains. This equation 2 becomes H equals UT plus half GT squared. And this one also, it means here that our U, if we are considering this very way, our U this one remains okay, this one is alright, but for this, well, let's come to this aspect now. I want to make some another adjustments. We look at the downward motion when they're falling down. We consider these very aspects. We have V equal to U plus AT. Then, let's assume the body was not falling freely from rest. Let's assume it's not falling freely from rest. Then we can say here that this equation becomes V. It implies that we have V equals U plus GT. If it's not falling freely from a height above the ground, and for this one too, it becomes H equals UT plus half GT squared when it's not falling freely when it's thrown from a height above the ground. Then you have you have it this way, and for this one you have the same thing here, V squared, almost the same thing. V squared equals U squared plus 2GH. As when it's not falling freely but thrown from a height above the ground, then you have it this way, V squared equals U squared plus 2GH. Now we want to make some kind of analysis. We want to analyze some things here. What are those things we should analyze? There are some things we shouldn't forget. When a body is falling freely above the ground, U is equal to 0. That is, the initial velocity is equal to 0. And when a body is thrown to a maximum height, when a body is thrown or an object is thrown from the ground to a maximum height, and then it stops its motion, it slows down to the maximum height, what we have, final velocity V is always equal to 0. Then whenever we have on the other aspects, when you consider our linear motion, when you consider the linear motion, when the body is moving on horizontally and it's coming from rest, our U is always equal to 0. Then when a body is moving, a moving body is moving towards rest or is slowing down, retarding, slowing down to rest, then the V, final velocity, equals 0. Then let's come to another aspect again. Whenever you are asked to look for the time for a free falling body, the time it takes a body to fall freely to the ground, then you can bring out some derivations. Very, very important. The time it will take a body to fall freely to the ground. That means we are trying to say time for a free falling body. The time for a free falling body. What is the expression, or what can we use to actually, which was the formula for calculating the time for a free falling body? What we have now here is we consider it this very way. H equals UT plus half GT squared. That is, when we look at what we have here, we can say from this side we have it this way, UT plus half GT squared. A body falling freely. When a body is falling freely from a height and then it strikes the ground, what time will it get to the ground? What's the time? At what time? Then we can say from falling freely from a height, U is equal to 0. We fix it here. It implies that H is equal to, now U is 0 times T, and this makes plus half gt squared. Then it implies here that h is equal to half gt squared, making your, then when you transform that, you have 2h is equal to gt squared. Then our t squared is equal to 2h all over g. It implies here that time t is equal to, then you have square root of 2h all over g. This is the expression, or this is what we have. It's formula for the time for a free falling body. The time it takes a body to fall freely from a height to the ground level. Here we also look at it again. What about the velocity? The formula or the expression for calculating velocity of a free falling body. When the body falls from a particular height above the ground to the ground level, then what happens? We consider it from this very expression. From this very expression we have v squared equals u squared plus 2as. Now remember, it falls freely from a height above the ground. Falling freely means that our u is equal to 0. Then what do we say about that? Then we can write here, say that v squared is equal to 0 squared plus 2gh. Therefore, you can say v squared is equal to 2gh. And you can say also v is equal to the square root of 2gh. And that's what we have in equation 6. Then another way, the other aspect of it is this: v equal to gt. When you are considering the formula for a body falling freely to the ground, and what's the velocity for a free falling body? Velocity v is equal to gt, or you can say velocity is equal to square root of 2gh based on the parameters given to us. Now, finally, let's now see some kind of conversion we should always consider. Whenever you are given, at any point in time, you are given a value, the velocity, either final velocity or the initial velocity, and you are asked to actually convert, or you are asked to solve a problem, and that velocity given to you is in kilometer per hour. You are asked to put your answer in meter per second. Then you have to do some conversions. And what are the conversions? Look at it very well. When you are converting kilometer per hour velocity in kilometer per hour to meter per second, what you gotta do is just very simple. Look at it. For instance, you are converting, let's say you're converting velocity in kilometer per hour to meter per second. Then what you're going to do, for instance, when you are given, let's say if velocity is equal to, let's say 72 kilometers per hour, and you are asked to leave your answer in meter per second. Just make it easy, so easy. 72 kilometers per hour, or means 72 kilometers all over hour, 1 hour. Per hour means 1 hour. Then it implies that v, which is equal to 72 kilometers all over 1 hour. That's mean. But remember, how many meters make 1 kilometer? That's 1,000 meters makes 1 kilometer. So you will have to multiply 72 kilometers by 1,000. When you multiply it, what you have now is 72 times 1,000 all over. Here is 1 hour, and then you are changing an hour to seconds. How many seconds are there in 1 hour? 3,600 seconds are there in 1 hour. So you're going to write like this: 3,600 seconds are there in 1 hour. Then at the end of the day, 0 cancels to 0, 0 cancels to 0, and then you have 36 going here 1, and 36 here is 2. So that's what 2 times 10, that's 20 meters per second. It has been converted. Generally, you can now summarize it this way by saying, if you are given, for example, x kilometer per hour, you have to change it to meter per seconds. All you're going to do is to say is equal to x kilometer, that x value times 1000 all over the hour now, which is the seconds, 3600 seconds. And when you do that, you do your cancellation or your division. At the end of the day, you have 10x over 6 meter per seconds, or you can say 5 over 18 meter 5x over 18 meter per seconds. 5x over 18 meters per second. That means that's the process to follow, how to convert from kilometer per hour to meter per seconds. Now we will, in the next class, we are going to consider the various calculations. Now we'll consider various types of calculations to do with linear motion and as well as the motion under gravity, that is upward and downward motion. So get yourself ready. We'll get ourselves ready with different type of questions. We're going to solve and make ourselves satisfied with various kind of calculation that actually concerns linear motion, horizontal motion, as well as vertical motions. And here we are going to get to the top. Nothing is difficult.